Today as we go through things, we're doing section 4.1 and 4.2. We're doing scatter plots. We're also doing lines of best fit or linear regression is what we're doing. We have done scatter plots before in our life. So creating a scatter plot, I'm not too worried about. I know you guys can look at a table of numbers, put dots on a grid, and then label the X, Y axis and so forth. So we have like one example of doing those. It's some of the other things is where some of us may have not gotten stuff in Algebra 2 when standards changed on talking about the linear correlation. How do we interpret it and compute that actually physically? And then determine, hey, is there a linear relationship between the two variables besides just looking, does it look like the dots are in a straight line? There is a process that we actually go through to do that. So, and then we actually get to talk about in this one the difference between correlation and causation. So then we'll get into the next line where actually we create the lines of best fit or the LSRL, least squares regression line. Again, we know a scatter diagram or a scatter plot is a graph that shows a relationship between two quantities of variables measured on the same thing. Basically, it's based off of an explanatory variable and a response variable. So as you draw your graph, one, you have to make sure you decide when you're given the freedom which variable is the explanatory, which variable, kind of is the independent variable, and then which one is the response. The response variable is your dependent variable, where we're trying to determine what this result would be based off of this other thing already occurring. So your explanatory variable goes on the horizontal axis. Your response variable goes on the vertical axis. Just like we did with independent on the horizontal and dependent on the vertical. We don't have to do a 4-quadrant graph. We can just stick with what's in the top right-hand corner. Scatter plots, there are some leeway on not having the scale start at 0 on both things and just going from 0, 5, 10, or whatever. When you have data that's a lot larger, and then we need to have a little kind of stutter step, and then we start a constant scale. We do want to have a consistent scale on the horizontal vertical axis, but we don't necessarily have to start at 0. Because sometimes our data may be in the hundreds or thousands, and there's no sense to have this humongously big graph that's the size of a parking lot in order to go through and do stuff, okay? Or when we squeeze it on a piece of paper, we have a scale of going by 1,000, so we really can't tell what's going on, okay? So and that's where we kind of have a little leeway on how we scale things out. So again, knowing that you know how to plot dots on a grid, a golf pro in an example wants to investigate the relationship between the club head speed of the golf club measured in miles per hour and the distance in yards that the ball will travel. So right there, they tell us the relationship between club head speed and the distance it travels. So with that in mind, the explanatory variable is the club head speed, and the distance that it travels is my response variable. So that lets me know that how I'm going to go ahead and start setting up my scatter plot. I try to make it a little bit easier, putting a scale on there for us and label the y-axis here in a little bit. But that's how we would go back to talk about how do I assign which one causes the other. Can the distance traveled dictate the speed, of the club head? Well, no, because we got to hit the ball first. So that's where when we look at situations, which one kind of causes the other one is what we're going to look for. And that's a good way to kind of do the explanatory and the response. To eliminate the variability due to these variables, the pro golfer used a single model of a club and ball, one golfer, and a clear, nice little 70-degree day. He was trying to get rid of all the little lurky variables that could affect stuff that goes on there. The pro records the club head speed, measures the distance and ball travels, and collects data. They want us to draw the scatter plot, then kind of interpret what do we see going on there. So again, each one of those things are an ordered pair. So it's just a matter of quickly just sketching in here where it is. Again, we can get a good idea. We're going to do it in the calculator here in a minute too, because we're going to use that data multiple times in this lesson so we don't have to keep retyping in tables. So if you can do me a favor, if you can just quickly sketch that real quick, put the dots on there. Oops. I'm going to catch up to you too. There we go. So I think I got all the dots on there. Again, it's a rough estimate. You know, if we had graph paper and grid lines, we could probably get more accurate with it. Again, I'm not worried about that from that standpoint. I think on homework stuff, and typically on a test, you know, I would have these as a multiple choice where you pick the right scatter plot for it, you know, as opposed to you hand doing it, just because it takes a while to put a lot of dots on there and eats up a lot of time. Whereas it's the other part, the interpretation, sometimes the calculation stuff, we're more interested in, you know, your grasp of that as an assessment. So, you know, this part will be done for you on both, not only my chapter test, but also the final exam is what it'll be. So what do we see? When we interpret a scatter plot, we always talk about as the explanatory variable increases. So as the explanatory variable, as club head speed, speed has two E's, increases, the distance traveled does what? Does it increase? Does it decrease? As we start from the slower club speed up to a higher club speed, we notice that there is a consistent pattern as the club head speed increases. It is it's going up as a distance traveled. There's some odd things. There's the one where this little guy right here, that one right there is, hey, that was a slower club speed by a little bit, but still traveled a good distance, okay? But we can pretty much say here that as club head speed increases, the distance traveled increases as well. All right. Next, our scatter plots have showed relationships between the two variables. We've learned about these before. We threw out back when you were younger anything about a nonlinear. We just had choices: was it linear or nonlinear? Is what we had choices of. We actually in statistics get to go dig in a little bit further to, hey, is it a quadratic regression? Is it an exponential regression? For a nonlinear pattern, is it a logarithmic regression that's taking place between the association of the two variables? Again, as we look at the different types of correlation, the first one is a positive correlation because as the x increases, the y is increasing. So as the explanatory increases, the response, the y increases. So that's what we call a positive correlation. The next one would be a negative correlation. As the x increases, the y decreases. Therefore, we see a negative slope is what we see. The nonlinears get trickier. We really, you know, as of course, as we see as the next two pictures, as the x increases, sometimes the y is increasing, sometimes the y is decreasing. And that's why it's nonlinear. We don't get into, so, you know, we would in some cases at times say there is a positive and a negative correlation. It just depends on what the values are between. But then, you know, usually when we're associating, the positive and negatives to a linear correlation, you know, if it's consistently, you know, curved like a parabola, like sometimes we'll see a set of data that kind of resembles a parabolic curve like this, and that's like the right side of the parabola. And so we would say, hey, this is a positive quadratic relationship going on here. Okay. Again, those are different chapters actually outside of the course of this course is what we have to worry about. We don't have to go that far into it. How is the correlation computed? Here is the fancy formula that it is computed. So that's where I was talking about. You may want to go through and put this on that little note card, on that note sheet to have down there just in case you got to calculate that R value by hand. So what it is, and I have one way to show you how to do it by calculator method eventually, but that's when they give us all the data set. So what this formula is telling us is we got to find the mean of the Y values, find the mean of X values, mean of the Y values. Once we find those means, we take basically each X value, subtract the mean from it, divided by the standard deviation of the X's. And I got to do that for every single X value. And then I got to take, once I get those answers, and usually it's like one at a time. You do like the first X data value minus the mean divided by the standard deviation of X. Then you multiply that answer by the first Y value minus the Y mean divided by the standard deviation of Y's. Then you multiply those two answers together. And then you add them all up. That's what the summation means there. Then you add up all those answers together and then divide by n minus 1. And so when you have a large data set, that is a long process to do by hand. Even our little example up here would take us probably, to do it fully without technology, it could take us 15 minutes to do it by hand. Okay? Using technology, even the quick shortcuts, make it go quicker. We can do it, not using the fancy shortcut keys, but it would still take about 5 minutes to do it some other ways. Okay? So that's the first thing I would add to like a note card, is add something like that to it. Here are some properties of the linear correlation coefficient. First off, the linear correlation coefficient, what is known as the R value. That's what it's referred to, the R value. The R value is has to be between -1 and 1. It can't be bigger than 1. It can't be less than -1. It can be equal to. If you're equal to 1 or -1, that means you're like perfectly linear. All right? There is a perfect linear association in a way. But typically we're a range of decimals between -1 and +1. The closer you are to 0, that's where we have kind of a no correlation. Now we make a little note in here that just because R is close to 0 doesn't mean there's no evidence of a linear relationship. It's just that, hey, it doesn't imply there. So like in my other stats classes, based on their curriculum that they use, +1, 0, and then we have -1. So we have usually a little number line that we use, and we try to kind of put a little gauge on when can we use certain adjectives like, hey, there's a strong negative or a weak negative, and so forth. And so with that in mind, in those classes, I usually teach them just based off of, things that we do, usually around the like -0.7 and then +0.7. Anything between the 0.7s and the 1s, we get to use the adjective strong. So we get to say there's a strong positive or a strong negative is what we use as an adjective. And then the next kind of barrier is kind of right around like the 0.5. It's kind of small, but we can say like -0.5 and +0.5. We get to use in that range. We get to use moderate. There's a moderately positive, linear relationship occurring. And then usually what I have my kids do is somewhere down here about the -0.2, -0.2 and the 0.2, anything between basically the negative 0.2 and 5 and negative 0.5, we use weak. We use the adjective weak for that zone. And then between the 0.2s is pretty much where we kind of go with a no correlation. Now, every textbook, every author has a different interpretation on there, so you got to kind of get involved with, inside the chapter, reading it, all the little tips and so forth. And it's, as we talked about in previous courses, what's an example of no correlation? If I had, let's say I had the explanatory variable was I went around here, got everybody's shoe size. Then I took the score on your first test. And then I plotted a scatter plot based on shoe size and test score. And then we think about, hey, does your shoe size, can it give us an idea of what your test score would be? And we're like, well, no, it really doesn't matter. I mean, some people with large shoe sizes may score high. Some with large shoe sizes may score low. And vice versa, all the way between the lows and so forth. And so there are some relationships between topics that, hey, there's just no linear relationship. It's just a coincidence that, hey, this was taking place. Linear coefficients are unitless. They're not allowed to have any units on them. Those are usually like your multiple choice kind of questions where they say, hey, which one of these are valid or is not a valid correlation coefficient, an R value? Well, first thing we're looking for, hey, is it a number bigger than +1 or smaller than -1? Next thing we're looking for, did they put units on there? Because sometimes they do. They'll say the R value is 0.6 meters. Well, we can't have units on it. Okay, so we never tag a unit when we say or when we indicate what the R value is. Then also here, because and the reason is because the unit of measure doesn't make anything, has no role in the interpretation of the R value. The correlation coefficient is not resistant, so we put that in the category of your mean, your standard deviations. When we have outliers, then they affect the correlation. Certain outliers in certain directions can make the correlation be a lot stronger than it needs to be, or make it a lot weaker. Okay? And what I'll do is I'll make a little note to, I have an applet that I use with my AP stats class that we can go online and we get to just touch on the screen, put a bunch of dots on there, and then we can start saying, well, if I put it, and it calculates the correlation coefficient based on where you put them, then if you add another dot here, you can see how it changes quickly the correlation coefficient and so forth when you do outliers in certain directions. Typically, outliers in the horizontal direction, so the x directions, have a greater impact on the correlation coefficient. Okay? So here we have, again, as we look at our ranging of values, just trying to give you a rough idea of, how would you assign a numerical value to the R value to a picture. I do have an example of that. I think I saw some on the homework, but also I think I have an example later on here where you just get to give some choices and you just get to match up, hey, this one looks like about this and so forth. First thing I would always do is look at directional. If it looks like there's a positive slope, we're looking for positive R values to associate with it. Then we look at the strength of it. This first example is a really nice, tight, straight line, so it should have a high correlation value. And it's positive, so it should be closer to +1. All right? This one is a nice straight line. However, it's not as strong as the first one. Okay? Again, I know that looks like a -1, but it's kind of blurry there. It's supposed to be a +1 is what that one is. That's an equal sign is what that little sucker is. So this next one here, if we drew the line of best fit, which would technically go through, or the least squares regression line is the terminology we use, the least squares regression line would probably be something like that. And then we talk about, okay, there is some vertical gap here between some of the values, and it's not super tight to that line. So that's why the R value is a little bit less compared to the other one that we just did. And as we draw the next one, I draw the next one and draw a least squares regression line through that one potentially. Notice how there's more vertical spread away from that purple line that I put in there. And again, the more vertical spread in a way between the dots or the data points and the line of best fit or least squares regression line, the lower the R value is. Okay, I would say we're strong on the first one, strong, and then this one we would say more of a weak is what we could say, weak positive. You always want to make sure you use directional, positive, negative. Again, they have some examples of the negatives there for you. And then when we're looking at the no correlations, when we have R values close to zero, sometimes we just can't tell that, hey, there's no association or correlation because they are so spread out. Sometimes as X increased, Y increased, sometimes it decreased. There's just no consistent pattern to say that something like that's happening. Here we can definitely see that it's definitely nonlinear, okay? It almost looks like, in a way, Y equals negative X squared. The quadratic graph upside down is what it kind of looks like as a correlation there. And there are some statistics classes where they ask you to try to do transformations on the data points, whether it's the X, the Y, the both, in order to make it a linear model. And that's one of the things my AP course we just did last chapter was do those things. So here's a quick example where you have 4 choices, 4 graphs, and you got to try to associate each one of those with one of those pictures. So let me give you about 20, 30 seconds to kind of fly through that. So, as again, I'm just trying to make sure we're managing time good. As I looked at the first picture, I noticed that it was a positive correlation going on there. So I ignored the B and C answers and said, all right. And I looked at the bottom picture. They're both positive. Well, the first picture looked a lot tighter. If I drew a line of best fit in the center of the data, it looked like those dots were a lot closer to that least squares regression line. So then I assigned D to be with that picture. And then that forced kind of the 0.7. There's more vertical spacing from a line of best fit in there, so that's why it got the 0.7. Then when we looked at the negatives, I looked at, well, there is a better negative pattern in the bottom right-hand corner. And then when I look at my last two R values of either negative 0.7 or negative 0.05, negative 0.05 means that there is a negative trend, but it's kind of really spread out and possibly to where there may be nonlinear. And so that's where I see, hey, this little curve is more of a nonlinear. And so I should be looking at an R value of somewhere around, in this case, negative like 0.1 to 0. I should be looking at something really small, okay? So that's why I assigned the C to that one and the B to the other one. You're never going to have to just look at a picture and just say, hey, give a number. They're going to give you a range of stuff to kind of choose and to kind of isolate towards it. All right, how do we, and this is where I was talking about before. I did this up earlier. In case you need to do it by hand, okay? Now, we do, the calculator does this in a split second for us. And I wrote down, little notes here on how we're going to do that in the calculator here in a moment. You got to compute the X bar, the S sub X's, and the Y bars and the S sub Y's, so standard deviation of the X and the Y's individually. You got to go through each of those individual steps. And then you get to plug in, once you get the sum of all those multiplication things, divided by n minus 1. Calculator, it's a lot easier. And that's why we're going to skip to that to go real quick. We're going to put our data in L1 and L2. and we're going to look for a function in the calculate menu that says Lin regression. Now, here's where I need you to be careful. This before you get ahead of me. The R value is what our correlation coefficient is. That is not always turned on. Whenever you reset a calculator, it's automatically defaulted alpha. So you have to actually turn it on in order, when you do the Lin reg, for it to show the R value. So with that in mind, because again, that's one thing we do is my kids reset them at the end of the day when you're using my calculators. And so then I encourage you guys to reset them. So I'm going to reset mine. I'm going to do a second plus 712. And that feature turned it off. It turned off it showing me the R value. Second plus 712 resets it, clears out all the tables, gets the graphing window back to normal, a 10 by 10 window. So now, if I go into the word mode, go into that button, scroll all the way down to where you see stat diagnostic, arrow over to on, and press on. Now that feature will be available to me. So that when I go to do my linear regression, the R value is going to pop up on the screen for me. Okay, so that's what we need to make sure we do. So help your neighbor go to mode, scroll down the stat diagnostic, and turn on. Eliza, which one are you using? Using one of mine?
Yeah.
Okay, you want to use mine from here on, because yours, you have to actually press, like, you have to get to the catalog feature, so it's like, you have to do, so then you're scrolling to find it through like 50 things. So you want to make sure, again, if you don't have the stat diagnostic feature, like I just did here with mode and easily getting that way, switch to using my calculator. Okay, I can show you on yours, but it takes a little bit more time. Okay. So that's the fastest way to do it. So now that we have that, I'm just going to quit the screen, and then we're ready to start doing a problem. And let me scroll that over there. Let me see what this is. Yeah. So we're going to be doing that here in a minute. Because I picked a few problems just to do these multiple tasks on that they ask us in some questions here. For determining if there is a linear relationship. Now, this is not in, those of you that had me for honors stats, this was not in that course. Even in my AP course, we don't go through this method to determine if there is a linear relationship. It's this publisher, author, and stuff of the college textbooks say, hey, this is what we're going to use as an extra method to determine if there's a linear relationship. Okay? So when I was doing my notes last night, I'm like, ooh, we better do some examples of this because that could be accountable on the test for the final for the semester. Okay? So what we do here is to determine if there is a linear relationship, besides looking at a picture, because sometimes a picture can be misleading, we first have to define the absolute value of the correlation coefficient, so that R value. We got to take the absolute value of that R value. So that means if it's positive, it stays positive. If it's a negative, we make it positive. Then we look at this table of numbers here, and I cut and pasted this table that was in the appendix. Okay? So we're using this one to compare to. And as I looked at homework problems last night, you have one here where they give you like 5 data numbers to do the stuff with, and then they have a second link to pull up this table is what they pulled up. So that's what I cut and paste from one of the homework problems, this table here. That way you can use it, so I wanted to put this in so you can do one of those homework problems. Now you compare it. Now you basically have to figure out, okay, what is the sample size that you're given? And you're going to go down to that line, whatever your sample size is. Is it 5? Is it 10? What is it? And then you're going to compare. If the absolute value of the correlation coefficient is greater than the critical value, these are my critical values. Those are my critical values. That's what it's referring to. Then a linear relationship exists between the two variables. Otherwise, no linear relationship. Okay, so this is a key thing to keep in mind. Once you get your correlation coefficient, we take the absolute value of it. Then we compare to whichever line we fall based on the number of samples. And we're going to do an example right now, or 2 of them, just so we can practice it before we do some other stuff, getting the R values. And then deciding, okay, is it that way? So 1, 2, 3, 4, 5, 6, 7. So our n is equal to 7. So eventually when we do this problem, we're going to pay attention to line 7 is what we're going to pay attention to. So I'm going to zoom in on my table, and I'm going to split screen so I can type we're assuming commute time would be the explanatory, and the health index would be the response. I'm saying that just from personal experience. The longer I've had to commute in my life for jobs and stuff, yeah, there's an impact on my life because of stress and how I was at that time. I remember being in college, long time ago, back in the early 90s, and my parents lived up in the Poconos, and I would drive 2 hours every morning to get into the middle of New Jersey and paint houses with a guy and then drive back that night. And so there was time, and I would leave super early in the morning at 5 o'clock because we started at 7. And then there would be times when I'm going through New Jersey and it's rush hour traffic, and we think Nashville's bad, but if you've ever been through Atlanta, the Northeast is just as worse and stuff. And so the stress of driving in that traffic, I could feel the weight in a way. With that in mind, let's go ahead and put those things in there. I'm going to split screen. And we go stats and enter. All right, so. I guess for us, it's like the coming to school in the morning. Do you get stressed out when you have all those big lines backed up, on Long Hollow or New Shackle trying to get to school and you're running late? All right, so I have those in there. And then now I go through and go 69.2, 68.3, 67.5, 67.1. Now here's where we got to be really careful typing in our data. We have to make sure we pair each X value with its corresponding Y value. If we don't, then we change what the line of the least squares regression is. We change the correlation. So here's where we got to be careful pairing up each X with each Y. If you ever get to the least squares regression feature that we're getting ready to do, and it gives you a domain error, that typically means that you don't have the same number of things in your X and Y columns. That's usually one of the indicators that you left one off, and there's not a match for it to do all these calculations with. So I got all my stuff in there. I'm going to press second mode. I'm going to go stat, arrow over to calculate. We're going to be, again, using this column a bunch now between our 1var stats. We're going to go to option number 4, LinReg. The next section uses this one as well. So we go to LinReg, hit enter. We confirm where's my X values, where's my Y values. We did put our X's in L1. We did put them in L2. If you by chance mixed them up, then you could change the classification there and you don't have to really retype your data, okay? We're going to go ahead and arrow down. We leave the frequency list blank. We'll talk about the store regeq in the next section. And I'm going to go down to calculate and hit enter. And then that's what it spits out. So it spits out, and we're looking at the very bottom number. Our R value is that bottom number, negative 0.9805. 4 digits, rounding to the 4th digit is what this whole chapter is based off. As I looked at notes, just kept referring, going back. Four decimal places, round to the 4th. So now there's my R value. We'll talk about the A and B and the R squared later. So now to decide is a linear model appropriate, I'm supposed to take the absolute value of that amount. So the absolute value of negative 0.9805. 805. Well, that means that's now positive 0.9805. And then I compare. Since I had 7 in my sample, I compare to 0.754. 0.9805 is greater than 0.754. Therefore, a linear model is appropriate. Okay. Now, that's a lot easier way of calculating the correlation coefficient than doing it by hand. Okay? And the only reason we would do it by hand is if they don't give us the data values and we have to use those formulas and so forth. But typically that would be for the slope and the y-intercept, just because there's so much doing, in order to get it for the summation stuff. I have one more example for you to practice in there. So, again, we have a total of 1, 2, 3, 4, 5, 6. So our n is equal to 6. So eventually we're going to pair that to the 6th line. So if we want to go in there real quick and do that one for me. Are those decimal points? Yeah. Remember, you can't put commas in the table feature here, just to let you know in the future. All right. And I'm going to hit Stat, Calculate, option number 4, go to the bottom, woohoo, and they tell me my R value on this one is a negative 0.9759. So now I have to do the absolute value of that. Then I get to compare. So that is going to be a positive 0.9759. And according to our chart up here, it was n is equal to 6 was 0.811. So 0.9759 is greater than 0.811. Therefore, a linear model is appropriate. Okay. Again, this next one is kind of there for you to do as well. We're going to hold off on that one. But drawing. The one thing we haven't done yet is drawing the scatter plot with the calculator. So just to show you how you can do a scatter plot on the calculator, if you don't know, in case you forgot. We go into our stat plot, so go second y equals, turn our stat plot on. So we enter on the first one, press on. The very first type is set up as a scatter plot. Then we just make sure we choose the correct X and Y list so it knows how to graph it. We hit the word graph. We're not going to see anything. We're going to do zoom 9. Zoom 9 is zoom statistics, and that puts it that zooms in on where is our data, and so it adjusts it. Okay, do we see a negative correlation here? Because our R value was negative, was a negative 9.8. It was a strong negative correlation. As the commute time increased, or in this case it was credit score. As credit score increased, the interest rate decreased, is what we can say on this last one. As the credit score increased, your interest rate decreased. Okay? And that's why we see all these things on ads about, increasing your credit score, because then when you go to buy a car or you go to buy something and you have to finance it, you get a better rate, interest rate, as they go to charge it. So, all right. So that again, the last one, if you want to do it, you can do it. If we get time, we can come back to it.